Fine. So we were talking about sensitivity. It is defined as the ratio of true positives and the total number of positive samples used in the training. So in that context, whatever be the number of authorized persons in the organization and how many did your machine learning system recognize as true positives, that means authorized, that ratio will come out as a sensitivity. If it had actually recognized 99 out of 100 people, the sensitivity would be 0.99. And if you want to take its percentage, it will be 99%. So that gives us a measure for this correctness. And when it comes to precision, it is computed as positive predictive value and is given as true positives divided by true positives plus false positives. You can understand that true positive is the actual value, false positive is the predictive value. So how many people are identified as true positive? That is what is actually correctly recognized. But this doesn't represent P. Actually, TP is not equal to P. So in total, how many of them were recognized as positive? And if you take this in the denominator and in the numerator you have true positives, that ratio is known as precision. So this is all the definition, and we go by the definitions first, and then we will look at different other measures of accuracy of the classifier models. What is specificity? As you know, this is the total number of true negatives divided by the total number of imposters. Total number of people who were correctly rejected divided by total number of people who were there in the imposter class. It is actually considered to be a two-class classification. Then we are having this kind of scenario. If you have a multi-class classification, then it will be a different computation. Okay. So then there is this term called as fallout. Fallout is a measure of false positive rate and is defined as 1 minus specificity. So basically it is representing this ratio of false positive divided by true negative plus false positive. Both of them represent the total number of people who were, what do you say, who were there in the imposter or who were there in the authorized list. What is this FP representing? Does it refer an imposter or does it refer a authorized? What is this FP referring to? False positive. That means it is an imposter is falsely predicted as authorized. What do you mean by true negative? True negative is referring to the imposter being recognized as imposter. So both of these terms are referring to the imposters, right? And what is this ratio? False positive divided by true negative plus false positive. This is what is fallout. These are all the terms which have been coined, and these represent certain specifications regarding the accuracy. And then there comes the measure of accuracy, which we all understand as a simple measure of seeing whether a person is classified as true positive or true negative. So this comes out to be an expression which is true positive plus true negative divided by true positive plus false negative plus true negative plus false positive. Yeah, true negative is actually, no, it is not referring to authorized. True negative refers to the imposter getting rejected. I can show you that table again to recall these terms. I'm coming to this. So what is true negative? It is the correct rejection. An imposter needs to be rejected. It is the correct rejection. Okay, Anish? So if you have to reject the authorized, where will it go? It will be the false rejection. That means it is a false negative, incorrect rejection. So for authorized, if you're rejecting, it is a false rejection. That means false negative. Are you clear about the difference between true negative and false negative? Okay. So then we are going to understand this accuracy. Right. So here again pick up these words. The true positive. This is the correct uh, acceptance of the authorized people. True negative, correct rejection of the imposters. That means this is all a total of what your classifier is expected to do. Okay, and how much it has done in terms of all the people, including all authorized and all imposters. How do you define all authorized out of these? Who will be the authorized people out of this? True positive, yes, and false negative. These are all those people who are authorized. And who are the imposters? True negative and false positive. These are all the, this number is constituting the total number of imposters. Am I right? True negative plus false positive is the total number of imposters, and true positive plus false negative is the total number of authorized people. Out of sum total of all, if my classifier is able to correctly accept all authorized people, that is true positive, and correctly reject all imposters, that is true negative, that ratio of the sum of TP plus TN divided by TP plus FN plus TN plus FP. This is actually the accuracy. Alright. Say for example, you are having a camera mounted on, top of the street light to check which vehicle came in, whether it is a bus or car, but actually you did not train your system with a bullock cart, and all of a sudden there is a bullock cart on the road. Your system must reject that, or must not recognize it as one of the classes that you have in your system, as bus or whatever, scooter or car. That will be a kind of imposter. Or else if you have a tank on the road, or or a helicopter on the road, which you probably did not use as one of the classes in your authorized data set, then they will be behaving as imposters. So it is just not the organization which can have imposters and authorized people. It can be the road where you are actually working with the data, where some of the classes are there part of your database. They will be the authorized classes, and there will be some which are unauthorized classes, where you do not have to really be worried about recognizing them. So that means imposters we did not consider in training set. Yes, we did not consider them in the training set. We did not take them in the model building. Yes. Okay. You can understand that your all such models which we have actually seen so far. You try to recall them. I'll show you how. If you recall them, we actually took some points. Yeah, I'm just trying to draw some lines. Just 1 minute. Actually, there is some noise in the background. I will just request them not to speak so loudly. Yeah, so let me continue. So actually I was trying to give you the scenario where imposters are also likely to be recognized as one of the valid classes. What is that scenario? Look at it, and then later on when we pick up the classification in the later half of the semester, we will talk about some classifiers where we have still scope of rejecting the imposters, while the classifier that we had just seen earlier, the KNN, or even the naive Bayes, or even decision tree, we still have chances that we are not rejecting the imposters. Try to keep in mind, and when we discuss after the midterm exams, um, you will understand the difference between the two types of classifiers. I will pick up one more color here, just taking red. Okay. Then you have a green boundary. I'm trying to pick up this boundary here. So I'm taking a scenario which we had been discussing for long. The two classes with a separable data set, let us say, and the data description is by two features. Let us say there is an imposter coming with this magenta color. With those two descriptions, what will happen? It will lie somewhere here and there, either of this side. I'll show you with this green color. I'm trying to pick up this imposter. Maybe its feature values are quite far away from your two classes data, but it will be lying somewhere either to this side of the boundary. Okay, it just cleaned the figure. So just give me some more time to draw it again. Yeah, please. So actually, instead of taking the wider brush, I cleaned it erroneously. So I am trying to draw these two class samples, and I'm trying to highlight here that there could be an imposter in this entire data, but it will not be identified through these classifiers which we had been discussing for long. I'm assuming that this is a two feature description, one on the left on the x-axis x1 and the other on the y-axis is x2. Whatever imposter it was, let us say if we evaluated maybe the bullock cart out of those two bus and truck classes, if I am evaluating bullock cart on its shape and different other features which I would have taken, if that bullock cart falls somewhere even here on the lower side of this boundary, I could classify it as the sample class of red pixels or red values. If it so happens that this bullock cart is falling even very far away from those blue points, because of the decision boundary, it is likely that we will classify it as blue points. So this kind of decision boundary is not giving us a scope for rejecting. This also is the kind of understanding I'm trying to create here, that the kind of linear or nonlinear boundary may not allow us to reject the imposters. You will see later that we still have better classifiers which will give us a way to reject by capturing the boundary around those samples, and anything beyond this boundary is an imposter, or anything beyond the boundary of these blue dots is a imposter. In that case, you can see that these green points are considered to be outsiders entirely. So this kind of classifier where I'm having a kind of elliptical or circular boundary, these classifiers are good for rejecting the imposters. But the classifier that we have been discussing for long, those being preliminary classifiers, are not having the capability to reject the imposters. Are you getting this point? Yeah. Can I get some response? So this kind of boundary, the red boundary in a circle or in a spherical way, would be known as radial basis function neural network. Some kind of demarcation between the data sample and some other outsider imposter can also be modeled using some complex classifiers. Of course, here today we are studying the way to evaluate the accuracy of the classifier, but try to correlate your understanding of the classes so far, that the classifiers that we discussed so far do not still have the capability to reject an imposter. These type of classifiers would come up later. Okay. So this is a kind of radial basis function neural network we will be trying to model later, and then we will have a way to discard the imposters even. All right. But of course, yeah, we should have the ways to evaluate the accuracy, and this is one measure. When you are not handling such kind of scenarios where you really worry about the imposter samples, then the total accuracy comes out to be a simple expression where it will be simply a true positive divided by true positive plus, what should it be? I'm not talking about the imposter's existence. How can you simplify this? Can you simplify? The total number of samples in the data set that can be there in the denominator. How would you treat that total number of samples? It is actually true positive plus false negative, something which is not classified correctly. So that will be there as the total sum of all the training samples, sorry, the test samples, right? So in simple terms, you can understand accuracy to be the count, that is the ratio of correctly identified test samples divided by the total number of test samples. That is where it will simplify if you are not handling the imposters. All right. So then there is one more method of understanding the classifier performance. It is known as confusion matrix. So a classifier performance is evaluated more precisely by an error matrix called confusion matrix. So the columns of the matrix depict the instances of the actual classes, and the rows of the matrix represent the instances of the predicted classes. The confusion matrix is also known as contingency table, and or otherwise some people call it as error matrix. So the performance of the classifier for two-class classification problem is visualized as a 2 by 2 matrix as is shown below, right? Here in this slide. So you have this table. So here you have actual classes where authorized, the positive, imposter, the negative. Similarly, how many authorized are recognized as authorized, that is what is the true positive. How many authorized are recognized as imposters is false positive. Should it be false positive, or it should be other way? What should be the predicted class? If an imposter is recognized as authorized, then it should be taken as false positive. So what is entered in the green square is correct. You can see that on the column side is the actual class. So if it is the imposter and is predicted as authorized, there will be false positive. So what is written inside this green square is correct. Similarly, when an authorized actual class, you can see that it is the first column, is recognized as imposter, then it is false negative. As you have understood the definitions, I think we need not give more time to this. You have understood the sensitivity and specificity, then positive predicted value and negative predicted value. These have their own formulae. So then we go ahead and look at what is a perfect classifier. So a classifier is said to be perfect if it produces non-zero values in the diagonal of the confusion matrix and has all zeros at the upper and lower triangular matrix entries. Okay. all the zeros. That means no class should be recognized as something else. No such test samples of one class be recognized as something else. So this means that the classifier is not confused and knows who is who correctly. A perfect classifier must not identify incorrectly an imposter, which means a perfect classifier must have false positive number as 0. Similarly, a perfect classifier must not incorrectly classify an authorized class data as imposter. That means false negative also should be 0, right? So FP is 0 and FN is 0 for the perfect classifier. Then what is the sensitivity value for the perfect classifier? It is true positive divided by true positive plus false negative. That means its sensitivity is actually 1, right? True positive is recognized as true positive. And fallout is actually 0 because FP is 0, right? So a perfect classifier is expected to get us the sensitivity value as 1 and the fallout value as 0. We will see their significance in a different form of the evaluation, which we call as receiver operating curve. So here is an example, right? Here is an example where we have 10 different classes, right? So that means your predictor has predicted three samples of class C1 as of belonging to class C1. That means your decision boundaries were so good that all the 3 were correctly recognized. C2's 4 samples were recognized as C2. C3's 5 samples were recognized as C3 correctly. But you can see that there were 3 samples belonging to class C7 but wrongly classified to be belonging to C3. In a way, it is a wrong classification. So that means any diagonal, upper diagonal or lower, upper triangular or lower triangular matrix, if it has a non-zero value, that gives the idea that your classifier did not perform good. But since everywhere else it is a 0, 1 or 2 sparse values can be accepted, but most of them are correct. The diagonal has all the non-zero values. Yeah, the question I'm taking is it sensitivity or specificity? So previously, you can see that a fallout is 1 minus specificity, right? And yeah, this one should it be sensitivity or specificity? Let us go back and check out the definition. What is your definition of specificity? Yeah. So what is recall? Sensitivity is recall. And true positive divided by true positive plus false negative. TP divided by TP plus FN. Right? So I am coming here. TP divided by TP plus FN. This is what is sensitivity, and this is going to be 1 in case of FN being 0. And fallout is 1 minus specificity, not the specificity. Okay. So now what do we see? 5 out of 8 were correctly classified. Are we talking about C7's 8 samples? 3 were misclassified to be belonging to C3 class, but 5 samples belonging to C7 class were actually correctly classified to be belonging to C7, right? So this is the error. Okay. So confusion matrix gives us a way to understand your classifier's performance. Then comes the receiver operating characteristic curve. ROC curve is a graph between false positive rates and true positive rates, which are plotted on x-axis and y-axis respectively. The false positive rate is also known as fallout and is equal to 1 minus specificity, while true positive rate is measured as sensitivity. So basically it is a graph between fallout and sensitivity. And you have seen earlier that the perfect classifier has sensitivity equal to 1 when fallout is 0. So when you look at the receiver operating curve, operating characteristic or ROC curve, you have TPR equals 1 and FPR equals 0. The curve with an observation resulting in extreme upper left corner point on the ROC, that means true positive rate or sensitivity is 1 and fallout is 0, is said to display the performance of the classifier as perfect. Let us look at the kind of ROC curves we can have. If we have a kind of plot between this 1 minus specificity, fallout, and true positive rate, then we are likely to get curves like this, right? Or we are likely to get curves even like this. So the curve like this, which I just drew, the one which is going through the upper left corner, is considered to be the one representing the best classifier we have. But if this curve is something like this, we would say that it is not so good a classifier. The one in between, or let me just try to the one which I am trying to draw here in blue color, let us say, or this one, sorry, this one is still showing us a better classifier. Okay. So what we are doing here is the classifier with the fallout and sensitivity taken as point P is said to be performing worse as P falls below the dotted line. You can look at this and see if there is a P point here, then this point is actually considered to be the one corresponding to the false positive rate here and true positive rate here. This classifier is considered to be the bad classifier. Basically, it is with respect to some parameters, right? And if there is this point Q that is falling above this line, we would say that the corresponding false positive rate and corresponding true positive rates are giving us a better classifier. Of course, this again is corresponding to another set of parameters, right? Why is false positive rate varying? It is because of the variation in some tuning of the parameter. Some parameters are changing, right? Here also this sensitivity is changing because of some parameters. So if there is a point Q or point P, you can refer to those fallout and those sensitivities which are corresponding to one set of parameters, right? So this will come by more experience and studies to visualize classifier design, okay? So if observations about the classifier performance are taken for a varying parameter, the ROC graph must stretch from lower left corner to the upper left corner of the graph and then to upper right corner. And the area under ROC curve for a perfect classifier ideally is equal to 1, while it is 0.5 or less for an imperfect classifier, right? So when you will work on any machine learning project, you try to make use of these parameters, these performance metrics rather, to showcase the abilities of your classifier, how good the classifier is. You can say that I have taken a cross-fold experimentation of 10-folded runs, and overall 10 runs I am getting an average accuracy or average sensitivity as 95% or 0.95 with a standard deviation of, let us say, 0.5, or let us say a standard deviation could be 2, right? That kind of projection of the performance of your classifier will be considered as a well investigated classifier. But if you just say that my accuracy of the classifier is 99%, it will not be considered as seriously a good classifier, right? Even though your classifier performance is low as 95%, but if you are talking about the stability or robustness in terms of your variances and the multiple folded experiments, then your machine learning project will be taken good, right? So what next? Here is a very simple display of the ROC curve taken with three different methods in one of the experiments that I did earlier. So PSO based method for face recognition, and we had proposed some classifier, and then the genetic algorithm based method. So of these, you will see some trends, right? It doesn't mean that all the classifiers are bad for all parameters. Of course, you will see that PSO is almost performing as good as the one which we proposed. But you can see a clear demarcation of the classifier represented by black, that is GA-based classifier, which is a little below than the two different curves in red and blue. So this is a kind of way you can estimate the performance of your proposed machine learning algorithm when you compare with the results, right? So ROC, you will see that most of them are accumulating in the upper left corner. That indicates that their one particular set of parameters is giving a 0 fallout and 1 sensitivity. So most of them are close to 1, but yeah, of course, GA-based classifier was having a low sensitivity, somewhere close to 0.9, but of course with a 0 fallout, right? So that way you can compare your classifier performances, right? So this is all today. Yeah, I wanted to come back to one question regarding mid-semester exam. Can you repeat that question? Actually, it has scrolled up. I am not able to see. Regarding mid-semester, there was one question. I'll try to locate. Yeah, syllabus for mid-sem will be lecture 1 to lecture 8, of which today is the 7th. Tomorrow I'm going to discuss the overall coverage, or rather a kind of review of the work that we did in these 7 lectures, plus a few problems I will be discussing tomorrow. So the syllabus is lectures 1 to 8. Okay. Of course, I will upload this also sometime today or tomorrow on the portal. Yeah, Python questions will not be there in the mid-semester exam. Python, I am asking you to practice for your assignment, which I will be uploading sometime in the later, half of March month sometime. I will give you some more practice code. Okay, so Python questions will not be there in the mid-semester exam. About the questions for the mid-semester exam, you can understand that it is a closed book exam, and we expect you to be able to explain and be expressive in, giving a clear explanation of your understanding of the concepts. Sometimes it is about the terms, about the differences between two different concepts. Then there will be some problems, and you need to represent your understanding of the concepts while even answering the questions, right? Any other question? So I have actually uploaded the revised handout, so you can refer those books which I have mentioned, right? Yeah, the question paper will be of 30 marks. Okay. Lecture slides are mostly sufficient, yes. But of course, additional reading is suggested. So if you read more, your understanding of the concepts will be built more strongly. Yeah, syllabus will be up to tomorrow's class. The content coverage is lectures 1 to 7, that is till today. But tomorrow also I am going to discuss some problems for your understanding. So in total, lectures 1 to 8 will be there in the mid-semester syllabus. Okay. Yeah, Tom Mitchell's book is there for you. Wherever you feel comfortable, you can refer. Otherwise, you can see the lecture slides, lecture material, and there are a couple of more reference books whose references I have also marked in the lecture details in the revised handout. So try to pick up the best you can from all the resources. Fine. Any more questions? So tomorrow we will have the review session. So you keep studying your syllabus, and tomorrow we will meet at 2 to review the entire set of sessions. Fine. So I am closing it here. So have a nice day.